Good morning, gang. So sorry I'm a couple minutes behind here. My computer decided to do a forced reboot, but we are coming back. So there's the dot cam. Don't need this anymore. Okay, so here we are. Here's this. So today we're beginning our last portion of the course, which involves really two kind of things. Power series, which is what we're going to start talking about today. And then also we're going to look at some applications as we round out the class. And we're going to have to move fairly quickly because we lost some time earlier in the semester. So let's just get started. Some news regarding exam 2. So this will be graded. My rule is always 1 week, so no later than this Friday. If you missed exam 2, for any reason, even if we already talked about it, please send me an email or Canvas message. That way we can sort out the makeup exam, right? So if we have already talked about it and I told you, yeah, that makes sense, we'll do a makeup, that's dope, we'll do it. Still message me anyway. That way I can get everything nice and organized into a single thread in my email and make sure everything works for everybody. If we haven't talked about it, especially though, if you know something happened and you just weren't able to get there on Friday and we haven't talked about it, really need to send me an email or a message because we don't want to be cruising out without having taken the test. We really don't want that. That could be really bad for your grade. So let's get those makeups sorted out. If you need a makeup, you need to reach out to me, and I'll do my best to be accommodating. And yeah, that is it. All the grades for exam 2 will be in this Friday. I'm not anticipating any rewrites or anything like that because we had all that extra time built into the test this time. So that's that today. We're going to talk about section 11.8, which is on power series. And most of this week, in fact, will be power series. Wednesday, we will do 11.9 and 11.10 will come on Friday. It's all power series. After we finish power series, we're going to talk about polar and parametric stuff. So you may remember from your trigonometry and pre-calculus classes, those topics, polar curves, usually discussed in trig, and parametric coordinates, parametric curves usually discussed in pre-calculus, or if you take 1147, we talk about them together. We're going to see how to do calculus in those settings in Calc 2. So those are the last topics. So power series rounds out the middle third of the course, and then polar and parametric stuff, some other applications at the end. So what is a power series? The definition, a power series is an expression of the form sigma n from wherever to infinity, Cn times x minus a to the n. So you've actually seen some things like this. In some of your earlier homeworks, we saw some questions that asked you, like, for what values of x does the following series converge? and it might have looked like 2 to the n times x minus 1 to the n or something like that. Those were actually power series. So the name for any series that can be written as some sequence of numbers times x minus some number all to the nth power are a power series. The number a is called the center of the series. And the sequence Cn is called the sequence of coefficients, or I should say are called the coefficients. All right. So the big deal here is that you're introducing a new variable, right? You've got the variable x in your series now. These are basically big, long polynomials. They are polynomials of infinite length. And the reason we like to study power series is because it turns out, given any nice function, you can find a power series which, for every particular value of x in some interval, converges to the value of that function. In other words, you can find an infinite polynomial that is equal to any nice function. Why is that dope? Well, because polynomials are easy to integrate, they're easy to differentiate, they're easy to take limits of. All the stuff that we like to do in calculus is easiest to do with polynomials. So if you have some wonky function that's hard to work with, like sine, cosine, tangent, e to the x, log x, if you can express it as a power series, then you can go and do all that stuff by doing that stuff to the series instead. And while it might look more intimidating, it's actually easier to do that stuff, integrate, differentiate, whatever, to a series than it is to most of these other functions. We need another definition before we can start. Associated with every power series sigma n from 0 to infinity Cn x minus a to the n is a real number capital R, which is greater than or equal to 0, called the radius of convergence. And not quite, Simon. So the idea here is not going to be that this is a hard way to do something that we'll learn how to do easier later. In fact, this is kind of the easy way. And what I'm getting at is that you've been integrating the hard way. And in a very real sense, the easy way to do an integral of a function is to first write the function as a power series, then integrate that series. Okay. So associated to every power series is a real number R, which is greater than or equal to 0, called the radius of convergence, such that the power series converges absolutely on the interval a minus r to a plus r, which is a symmetric interval. This interval is centered at a and has radius r. So let me draw the picture and you'll see why a is called the center. If you plug x equals a into this series, then this piece is a minus a is 0. So you just have Cn times 0 to the n, and at best, that's C1 or C0. So that series is guaranteed to converge if you plug in A. And then the question is, how far away from A can X be and still get a convergent series? Nala, kitty, get out of there. Nala. Nala, no. Out. No. Sorry. So the question is, if this series is guaranteed to converge when you plug in A for X, how far away from A can you wander and still get a convergent series? And the answer is R. So over here is A plus R, and over here is A minus R. And this distance is called the radius of convergence. And it's the same whether you measure it on the left or on the right. If you're studying these things in terms of complex numbers, if you let X be a complex number, then instead of a nice interval like this, you actually get a disk in the complex plane. And then this radius really is a radius of a circle. Yeah, she's a bad kitty sometimes. All right. Finally, one more definition. The set of all X values such that the power series sigma Cn x minus a to the n sum from 0 to infinity converges is always an interval symmetric about the center symmetric about the center called the interval of convergence. Sorry, converging C convergence. R is the radius of convergence, yeah. And then the interval of convergence, because it is always symmetric about the center, it's always one of the following. It's either the open interval from a minus r to a plus r, or left closed a minus r to a plus r, right open, or left open a minus r to a plus r, or closed on both sides. So your interval of convergence always looks like one of these guys, where A is the center and R is the radius of convergence. On the open interval, you're guaranteed to converge absolutely. At the endpoints, you might diverge, or you might converge conditionally, or you might converge absolutely. You can't say a priori, it depends on the series. But these are the basics of power series. Questions on what any of these definitions are describing? If the interval of convergence is open, then the series necessarily diverges at both endpoints, Because the interval of convergence is defined to be the set of all x values such that the series converges. So the convergence of a series like this depends on what you're trying to plug in for x. Right? This series, if you plug in x equals a, is guaranteed to converge. If you plug in x equals 5, it might not converge. So we want to give a name to the set of all x's I can plug in and get a convergent series out. The name for that set is called the interval of convergence. That's what we're defining here. So if the interval of convergence is closed at both ends like this, that means if you plug in any of these numbers, you'll get a convergent series. If the interval of convergence is open at both ends, that means you can only plug things in that are strictly between a minus r and a plus r. So if you plugged in a minus r, if this is your interval of convergence, then the series would diverge because a minus r is not an element of this set. So let's look at some examples. Sorry, I was doing some Riemann sum calculations with my Calc 1 class, so if you see, try to keep it out of field. Here. All right. So let's find the center, radius of convergence, and interval of convergence for the following power series. There were some similar concepts in homework 8. Yeah, that's what I was saying. So you've actually seen some power series before. This precise problem you've seen before, believe it or not, back in homework 8. I think that's what Lucas is referring to in the chat there. Of course, you may have had different numbers. But your first step is to recognize, the easiest way to solve this one is to recognize that this is the same as 1/2 to the n times x minus 3 to the n, which is sigma n from 0 to infinity, 1/2 times x minus 3 to the n. This is actually geometric. With common ratio, and I'm using little r here for the common ratio, the radius of convergence is big R, 1/2 times x minus 3. Okay, so the series will converge as long as the absolute value of this is smaller than 1. I almost forgot though, what's the center? Can anybody identify Cn, the coefficients, and the center, A? What is the center, A? Good, yeah, the center is 3. And the sequence of coefficients, Cn, what are those? It's not quite 1/2, it's 1/2 to the n, or 1 over 2 to the n. Okay. So, because my series is geometric, the series will converge provided absolute value of R is less than 1, which is equivalent to saying the absolute value of 1/2 times x minus 3 is less than 1. And now we need what are called unpacking rules for absolute value inequalities. I'll say recall the absolute value of some stuff is less than the positive constant c means negative c is less than that stuff is less than positive c. So when I teach this in college algebra, I call this an unpacking rule for the absolute value inequality. You'll need to remember this. We're going to use this a lot. So if you want to solve the absolute value of some shit is less than 5, you say -5 is less than that shit is less than 5. And then you solve the compound inequality just like you would in an algebra class. So here, my absolute value inequality unpacks as -1 is less than 1/2 times x minus 3 is less than 1. Now, if I want to solve this inequality for x, that means I'd like to get the middle to just have x. So I need to get rid of the 1/2, I need to get rid of the 3. Following my normal order of operations, I got to get rid of the 1/2 first, so I multiply through by 2. And I get -2 is less than x minus 3 is less than positive 2. And then I add 3 everywhere. So I get -2 plus 3, that's 1, is less than x is less than 2 plus 3 is 5. So the series will converge. This power series will converge if 1 is less than x is less than 5, i.e., if x is from the interval 1 to 5. And because this is a geometric series, I know that if this inequality is not satisfied, the series will diverge. Normally, at this point, I would say you need to check the endpoints. If I came up with this any other way, if this wasn't a geometric series, we would have to test what happens at the endpoint. Let me draw the picture here. My center is 3. And over here I have 1. Over here I have 5. So what is the radius of convergence? Two. Good. This distance, which is the same as this distance, even though I've drawn it badly. So the radius of convergence is r equals 2. And I think that's everything we wanted, right? I have my interval of convergence. I have my radius of convergence. I have my center. And I even found the coefficients, Cn. Oh, I'm sorry. Okay, is everybody back? Lucas says Zoom crashed. I don't know if that was on your end or my end, so give a second for folks to come back. Give me a thumbs up react if you can see everything. Okay, it looks like most people are good. Okay. Okay, sweet. So any questions about the calculations we did here? Okay. Let's do another one. Only this time, the series won't be geometric. Let's find the center. I'm going to use ROC for radius of convergence and IOC for the series sigma n from 0 to infinity, -1 to the n over 2n plus 1 times x to the 2n plus 1. Almost, Ryan. If x is not in the interval of convergence, then the series diverges. Yeah, that's the definition of the interval of convergence. If x is not in the interval of convergence, then the series diverges. So this series will converge if and only if x comes from this interval. So this interval is my interval of convergence. There's a lot of terminology here, right? There's a lot of notation and definitions and stuff. So a lot of vocabulary that we're learning. Here the center is 0, good. The center A is 0. Just for fun, let's write out the first few terms of this series. This is -1 to the 0. If I plug in n equals 0, I get -1 to the 0 over 1 times x to the 1. So this is x. And then -1 to the 1 is -1/3 x cubed. And then plus 1/5 x to the 5 minus 1/7 x to the 7 plus 1/9 x to the 9 minus blah, blah, blah. So this is what my series is if I write it out. And you see what I mean by these things being big, long polynomials, right? This is a polynomial. In fact, this polynomial happens to be arctan. This is arctan of x, believe it or not. And I'll be able to prove that to you soon. But it's only equal to arctan if the series converges. So we got to be able to figure out where the series converges. This is not a geometric series because I don't just have a bunch of shit all to the n. There's no way to rewrite 2n plus 1 as something to the n. And this guy, I might be able to massage this as like x squared to the n times x, but it's not going to work out because of the 2n plus 1. Because remember, the center is like the x minus a piece. So there's a couple weird things here, right? Rather than having like x to the n or x minus 5 to the n, I've got x to the 2n plus 1. But if you look in here, this is just x, this is just x, this is just x, this is just x. So rather than having like x minus 1 cubed, x minus 1 to the 5, x minus 1 to the 7, this is like x minus 0 cubed, x minus 0 to the 5, x minus 0 to the 7. So the thing that's being subtracted from x before you raise it to the power, that's always your center. It's a little bit weird. We could maybe try an alternating series test because this is an alternating series, but figuring out whether this piece is decreasing or increasing is weird. It's going to depend on what you're plugging in for x. So what I would rather do is jump in with my ratio test, and that's usually what we do for power series. So my next move is a ratio test, and this is almost always what you will do for power series. If the series happens to be exactly geometric, you can do what we did on the last example. But otherwise, if you're looking at a power series and you want to find radius or interval of convergence, you'll pretty much always use the ratio test. So here L is the limit as n goes to infinity of an plus 1 over an, which is the limit as n goes to infinity of an plus 1 is negative 1 to the n plus 1 times x to the 2n plus 1 over 2n plus 1 plus 1. That's an plus 1. And now I'll multiply by the reciprocal of an to divide by an. That's 2n plus 1 over negative 1 to the n x to the 2n plus 1. So this is my ratio test limit. If I distribute the 2 down here and here, 2n plus 1 is 2n plus 2 plus 1 is 2n plus 3. So this is lim n to infinity, absolute value, negative 1 to the n plus 1, x to the 2n plus 3 over 2n plus 3 times 2n plus 1 over negative 1 to the n x to the 2n plus 1. Now I'm going to rearrange my terms to put the like stuff with like stuff. And I get lim n to infinity, absolute value, negative 1 to the n plus 1 over negative 1 to the n times 2n plus 1 over 2n plus 3 times x to the 2n plus 3 over x to the 2n plus 1. Everybody with me so far? This is negative 1. This has limit 1. This is x squared. So I'm just going to do the algebra at this step. I won't do any of the limit taking. Because before I do any of the limit taking, I want to do something with my absolute values. Remember that absolute value is multiplicative, meaning it plays nice with multiplication. So this is lim n to infinity, absolute value of negative 1 times absolute value of 2n plus 1 over 2n plus 3 times absolute value of x squared. And only one of these pieces depends on n. This piece is just straight up equal to 1. And 1 times anything is just that thing. So what I get is this piece is constant with respect to n. So he can come outside the limit, and I get absolute value of x squared times the limit as n goes to infinity. 2n plus 1 over 2n plus 3 is positive, so I can lose the absolute values on that piece. So at this step, I'm dealing with the absolute values, and it's important that you do this. You have to figure out where the absolute values matter, and they definitely matter here. And you have to figure out where they don't matter. And then you can take your limit. So as n goes to infinity, 2n plus 1 over 2n plus 3 goes to 1. So this is just absolute value of x squared. Everybody with me? So this piece could pop outside the limit because he doesn't have any n's in him. This piece is constant, it's just 1. And this piece, as n goes to infinity, becomes 1. So this whole limit here is really just equal to this guy. That's because this piece here goes to 1. So this is abs x squared times 1, if you like. Fernando asks a valid question. Why do I care about the absolute values on the x squared piece? Because x squared is positive. It's not so much, you're right. You could say that here I don't care about the absolute values, but what I'm trying to say is that when you run this process for any power series, when you pop out the x's, you always want to leave the absolute values on those. Because what we're going to come down to now is that L is the absolute value of x squared. So my series will converge. You have to solve the absolute value inequality. My series converges absolutely, provided L is less than 1, which is equivalent to saying, and this won't always be an x squared, right? Sometimes this will be something else, and then the absolute value is really important. So it's good to be in the habit of leaving the x stuff with the absolute value. So Fernando's question is good there. Why do you need the absolute value of the x squared? In this particular problem, you could get away without it. But in general, when working with power series, you want to make sure you leave the variable stuff, the x stuff, in the absolute values, because your last step here is going to be to solve this inequality. L is less than 1. And if you forget the absolute values there, you can get into trouble. So for this particular problem, you could have gotten away without them, but I want you to be in the habit of leaving them there. And then we had a question about the algebra on this line. So what I did here is just shuffle like terms with like terms. I had a -1 to the n plus 1 upstairs and a -1 to the n downstairs. Since everything is being multiplied, no addition, I can just regroup as I choose. So I put the -1 powers together. I've got a 2n plus 1 upstairs and a 2n plus 3 downstairs, so I put those together. X to the 2n plus 3 and x to the 2n plus 1, so I put those together. This guy and this guy, I just subtract the powers because I'm dividing. N plus 1 minus n is just 1, so this is -1 to the first power. 2n plus 3 minus 2n plus 1 is 2, so this is just x squared, and this guy stayed the same. Caesar asked a good question. How did I know to do the ratio test here? Because if I'm working with a power series, my first goal is to find the radius of convergence. And the radius of convergence, remember the definition, gives you an interval over which the series is guaranteed to converge absolutely. And my fastest path to absolute convergence for a series is always the ratio or root test, unless the series happens to be geometric. So because I'm looking for all of the x values on which the series is guaranteed to converge absolutely, the ratio test is my fastest path. Also, the other tests would be really hard to run here because the other tests all involve something that would be complicated by this x. So because I have this extra variable x in here, I would have a hard time doing any of the other tests because it's hard to compare. I can't even imagine doing an integral test because normally you would replace n by x. But I mean, also this is alternating, so it's not positive. If you wanted to use the alternating series test, whether or not this thing is monotone decreasing would depend on whether or not x is bigger or smaller than 1. So you'd have to break it into cases. The ratio test is the easiest way for me to find where the series converges absolutely, which is the easiest way. So the ratio test is the easiest way for me to come after the radius of convergence. In short, for power series, we always use the ratio test. Ryan, you could say that, but it's not necessary. It's implicit. So we understand that if L is smaller than 1, the series will converge absolutely. If L is bigger than 1, then the series will diverge. If L is equal to 1, we don't really know. But for now, we just want to say the series converges absolutely as long as L is less than 1. So then I solve this inequality. So my next step is to solve this inequality. I can bring the square outside the absolute value, because again, absolute value plays nice with multiplication and powers. Then I can take square roots. And then I can unpack. So my series is guaranteed to converge absolutely for all x in the interval -1 to 1. I can draw that interval. My center here is 0. -1 is here. 1 is here. So my radius of convergence is 1. But I still don't actually know the interval of convergence. So remember, the interval of convergence is all the x values so that the series converges. What I know for now is that if you take anything from the open interval, the series converges absolutely. But I don't know what happens at the end points. So the last thing we need to do to identify the interval of convergence, we need to test the endpoints, which are x equals -1 and x equals 1. So I'm going to continue this on another page, but I'll leave this stuff here so you can still see it. Got all these wires in the way, fuck out the way. Okay, can you still see that? You can. All right. So in other words, at this point, my IOC for sigma n equals 0 to infinity, -1 to the n over 2n plus 1 times x to the 2n plus 1 must be one of -1 to 1 open, or -1 to 1 left closed right open, or -1 to 1 left open right closed, or -1 to 1 closed on both sides. Nala, Kitty, no. Nope. Yeah. Get out of there. Fucking shit up, Kitty. What did you do? No. Sorry about that. Okay. So I know that my series converges absolutely on the open interval. The question is, can I get more? Can I maybe include 1 in the interval of convergence? Because 1 is not a part of this set, right? These are all the numbers strictly between -1 and 1. And I want to know, can I bump out just a little bit more to include either of those endpoints? Is my IOC potentially closed on both sides? Closed on the right, open on the left, or closed on the left, open on the right? And to do that, we have to test the endpoints. So when x is equal to 1, my series is sigma n from 0 to infinity, -1 to the n over 2n plus 1 times 1 to the 2n plus 1. 1 to the 2n plus 1 is 1. So this is sigma n from 0 to infinity, -1 to the n over 2n plus 1. Does this series converge or diverge? It converges. It's a conditionally convergent series. It converges by the alternating series test. Here, the bn's are 1 over 2n plus 1, and I'll leave the details to you. So is x equals 1 included in my interval of convergence, or is it not included in my interval of convergence? Yeah. So that means my IOC is not this guy, because this guy does not include 1, and it's not this guy, because this guy does not include 1. So I can cross these out. And when x is equal to -1, my series is sigma n from 0 to infinity, -1 to the n over 2n plus 1 times -1 to the 2n plus 1. 1 to the 2n plus 1 is always 1. -1 to the 2n plus 1 is always -1. So this is sigma n from 0 to infinity, -1 to the n over 2n plus 1 times -1. Because 2n plus 1 is always odd, and odd powers of -1 are always -1. So this is the same as negative sigma n from 0 to infinity, -1 to the n over 2n plus 1. It's the same series, just with a negative out front. So this also converges. By AST. So -1 and 1 are both included. Therefore, the IOC, the interval of convergence, for sigma n from 0 to infinity, -1 to the n over 2n plus 1, x to the 2n plus 1, is the closed interval, -1 to 1. This is how these problems go. There's 3 convergence tests. You use the ratio test to find your radius of convergence, the open interval. Then you have to separately test each endpoint. And that will tell you whether or not to include either of the endpoints of that open interval from the ratio test. So each of these power series problems involves usually 3 separate convergence tests. Ratio test to get started, and then you plug in the endpoints and you have to decide what test to use for each of those. Sometimes it'll be an AST, sometimes it'll be another, well, no, it'll never be another ratio test. Sometimes it'll be an AST, sometimes it'll be a comparison test, sometimes you'll get a P-series. But always 3 separate convergence questions. Ratio test to get started, and then whatever test is appropriate for the endpoints. You won't actually ever use the ratio test for the endpoint work, because these numbers are necessarily the numbers that make L equal to 1. Because I started with the open interval, and then from this bit, I learned to include x equals 1. So let me write that down. Therefore, x equals 1 is in the IOC. And from this, I learned, therefore, x equals -1 is in the IOC. So if my question is, which one of these guys do I use? And I learned that 1 and -1 both need to be in the interval, this is the only guy that contains both 1 and -1. This guy contains 1 but does not contain -1. This guy contains -1 but does not contain 1. This guy contains neither -1 nor +1. So my little work here told me that it had to contain 1. So from the first bit, I learned that it can't be this guy and it can't be this guy, because neither of them contain +1. From my second endpoint work, I learned that -1 has to be in the series, so it can't be this guy and it can't be this guy. So the only one which remains is this guy. So remember, my question is, which one of these is my IOC? And the difference between these 4 intervals is only the endpoints, right? These are all intervals from -1 to 1. It's just that some contain one endpoint, some contain neither endpoint, some contain both endpoints. The closed interval is the one that contains both endpoints. And from my work here, I learned that the right endpoint, 1, should be contained in the IOC. So I can rule out anybody who doesn't contain the right endpoint. That's any interval that's open on the right. And from this work, I learned that -1 should be in my IOC. So I can rule out anyone who does not contain the left endpoint, -1. This guy does not contain -1, and this guy does not contain -1. So the only one that hasn't been ruled out, the only one that contains both endpoints, is the closed interval. Yes, the problems are getting long. This is just the nature of mathematics. Be grateful that you can solve a problem in a page and a half. Ryan asks, is it the case that the negative outside doesn't change anything? No, yeah, it does not, right? So I am finite and the negative version of me are finite, are equivalent, right? If something is finite, then when you slap a -1 on, that also must be finite. Or you could run AST again, right? That's another option. You could run through AST fresh for this series and fresh for this series. There's no harm in that, it just takes more time. So I'm trying to show you what I would consider to be a minimal acceptable solution. Okay, so if I ask you, find the interval of convergence for a power series, first you run the ratio test, then you check each endpoint. Once you've done all of that, you'll be able to tell me what the IOC is. Do not skip checking the endpoints. Common mistake, ruthless mistake. I want to show you a little bit what it looks like for a series of this sort to converge. So I'm going to come back to this page. and remind you that this is what my series looks like. Maybe I'll do this. So if you're still writing any of that old stuff, you can see it. I want to look at the partial sums of this series, right? This series, my series, written out looks like this. So the first partial sum is just x. The second partial sum is x minus 1/3 x cubed. The third partial sum is x minus 1/3 x cubed plus 1/5 x to the 5, and so on. So let's look at the sequence of partial sums for this power series. I'm going to tab over to Desmos. Okay, and I'm going to zoom way in here. These are the partial sums of that series, and they're polynomials. Everybody sees that, right? The first term plus the second term, first term plus second plus third term, and so on. I'm also going to graph here the inverse tangent function, and let me pick a color scheme that makes sense. Let's make this black. Let's make this something else. Let me make all these green. Okay. So black is arctan. Green is the first partial sum of my series. And I'm going to zoom into the interval -1 to 1. The green is actually the tangent line to the black at 0. Then if I look at the next partial sum, you see that this green is a little bit closer to the black than the first, right? Look at this gap over here. The gap here is larger than the gap here. So this green is a little bit closer to the black. The third partial sum, this guy, if you look at any particular x value, that gap is getting smaller and smaller. Here's the next partial sum, the gap's still getting smaller, and the next. If you look close to 0, anywhere from like -0.6 to 0.6, I can't even see the gap between the green and the black. That's what it looks like for a power series to converge. Because the partial sums of a power series are polynomials, they're not individual numbers, you have to compare the graphs. But as you look at longer and longer partial sums, this graph is getting closer to this graph. And that's the magic that's going on here. So let me zoom out a little bit. Here's the whole arctan graph. You don't know why this series converges to arctan yet, but I'll be able to show you soon. If you look at the first guy, the gaps are big. The second guy, it's getting closer, right? This is sticking to that function. It's like you glue the polynomial right here at 0, and then as you use more and more terms, it sticks further and further out. But the interval of convergence for this series is -1 to 1. So it only like glues to the graph. It only starts sticking to the black. The green only starts sticking to the black between -1 and 1. Outside that, the green and black will not come together. That's what the interval of convergence is about. So let me add one more here. The next term would be -1/11 x to the 11. See how the gap between the blue and the black is tighter than the gap between the green and the black. The blue is the next partial sum. And everywhere between -1 and 1, the blue is getting really, really close to the black. And it's closer than the green. So as you use more and more terms, your polynomials here get closer and closer to this function. That's the magic. You're finding polynomials that you could replace this weird function that's hard to work with by. For example, if I wanted the area from 0 to 1/2 underneath the black, I could just as easily find the area from 0 to 1/2 underneath the blue. Look, those areas are the same. If they're not exactly the same, they're real fucking close. Integrating arctan is hard. I mean, it's not hard, but you didn't know how to do it until Calc 2 because you need integration by parts. Integrating this blue function is easy. It's a polynomial. So if you wanted the area underneath the black curve from 0 to 1/2, this area, just integrate the blue polynomial instead because it's easier to work with. That's the magic of power series. That's why we do this stuff. Okay? So any questions on the calculation here? The ratio test work or the endpoint work? I think maybe my chat is being stupid. Let me see, are you guys typing things? I know it's closed brackets again. So the closed bracket thing came from checking whether the endpoints were included or not. Because at both endpoints, x equals 1, my series converges, and x equals -1, my series converges, I need to pick the interval that contains both endpoints, and that's this guy. -1 on the outside doesn't matter. Yeah, okay, so nothing fresh in chat. Okay, let's do another. This is a famous power series. This is the power series for e to the x. If you plug in n equals 0, you get 1 over 0 factorial, plus plug in n equals 1, you get x over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4 over 4 factorial, and so on. 0 factorial is 1. You know, I won't. So we can write this out. This is 1 plus x squared over 2 plus x cubed over 6 plus x to the 4 over 24, and so on. So it turns out that for reasons I'll be able to explain when we get to section 11.10, this is the series for e to the x. Lucas, what you're saying is correct, but we don't have any reason to justify it yet. So what I want to know is what numbers can I plug in for x so that this series converges? That's my goal, is to figure that out. X is definitely a variable, so we're thinking about plugging in all sorts of different things for x. But the question is, what x's can I plug in so that the series converges? Because the series only makes sense if it converges. So we run the ratio test. L is the limit as n goes to infinity of the absolute value of an plus 1 over an, which is the limit as n goes to infinity. So growth rates here still won't tell you whether or not the series converges. It'll just tell you whether the series passes TFD. Remember, that's important. It's true that based on growth rates, the series will always pass TFD, but it's not automatically true that the series converges. Remember, sigma 1 over n, the harmonic series, passes TFD, but diverges. So you cannot use growth rates to get convergence of series. An plus 1 here is x to the n plus 1 over n plus 1 factorial. And the reciprocal of an is n factorial over x to the n. So I want to come back to what Lucas was saying. Because n factorial grows faster than x to the n, can I say that this series always converges? No. Because n factorial is greater than x to the n, I can say for sure that this thing always goes to 0 as n goes to infinity. But that's not the same as saying the series converges. Remember, 1 over n goes to 0 as n goes to infinity, but the series sigma 1 over n diverges. So you could use growth rates to argue that this series always passes TFD. But remember, passing TFD is not the same as converging. There are lots of series that pass TFD, but still diverge, and the harmonic series is our prime example. So we need to run the ratio test. It turns out that what you're saying is not wrong. It's true that the series here will always converge, but you cannot conclude it using that logic. So let's reorganize the terms. I get x to the n plus 1 over x to the n times n factorial over n plus 1 factorial, which is limit n to infinity, absolute value of x times n minus 1 times n minus 2 all the way down to 3 times 2 times 1 divided by n plus 1 times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. And the whole of this numerator cancels with most of that denominator. So what we get out of this is lim n to infinity, absolute value of x times 1 over n plus 1. I can split up the absolute values as absolute x times absolute 1 over n plus 1. I can bring the absolute value of x outside. And 1 over n plus 1 is definitely positive. And now as n goes to infinity, 1 over n plus 1 goes to 0. So L, the limit from the ratio test, is the absolute value of x times 0, which is 0. Thus, L is less than 1 as long as the absolute value of x times 0 is less than 1, which is true for any real number x. So my series, hence the power series, sigma n equals 0 to infinity x to the n over n factorial converges Absolutely. For all real numbers x. Actually, Dalton asks a good question here. I just say real numbers because that's what we're working with. This works great for complex numbers too. Yeah. If you were considering variables as being complex numbers, it would be true for those as well. This series z to the n over n factorial is convergent for every complex number z as well. Yeah. In other words, you could omit the real here if you wanted. For any number x, real or complex. Hence, the power series converges for all real numbers x, i.e., the interval of convergence is negative infinity to infinity. And the radius of convergence we would say is plus infinity. And I'd like to do the same thing here where we look at the partial sums in Desmos. This particular calculation was not hard. So we won't see anything like within this interval, the functions start gluing, and outside the interval, they stop. But I'll give just a second for anybody who's writing here. There is a class at UF and at every university, as far as I know, called Functions of a Complex Variable or Introduction to Complex Analysis, where you'll study power series in terms of complex numbers. And there, everything actually makes a little bit more sense because the radius of convergence is really the radius of a disk. It's very nice. So let's look at these partial sums. Okay, I'll make them all green just like before. And then I'll add the original function in black and we'll zoom out. So the actual function here is, and I'll be able to show you why later. All right. So if you notice, the green and the black for the first partial sum only match right there at the center. The center of this series is 0. But as I start to add more and more terms, see now the green sticks closer to the black. As you wander away from the center, it gets less good, but as long as you stay close to the center, it stays very close. And as I look at more and more partial sums, the green and the black stay closer and closer. I'll come over here so we can see a little better what's going on. The next partial sum, look, as long as I'm between like -1 and 1, I can't even tell the green from the black. They look exactly the same. And as I give more and more terms in this partial sum, the next one would be x to the 5 over 5 factorial, which is 120. And then after that, it would be x to the plus x to the 6. 24 times 5 is 120, right? And the next one is 720. So here, the green and the black are almost indistinguishable, even from like -2 out to, shit, I don't know, way out here. Look, the green and the black stay really, really, really close. So there's my original function. Here's my first partial sum, second partial sum, third partial sum, fourth partial sum, fifth partial sum, and sixth partial sum. the area underneath the green from like -2 to 0 is the same as the area underneath the black from -2 to 0, or if not exactly the same, very, very close. If you let me use infinitely many terms in this series, then the green and the black will be identical. No, so here the center is still 0. Let's come back to the expression. So I never did write down the center, did I? This is sigma n from 0 to infinity 1 over n factorial times x to the n. So this piece is x minus 0 to the n, so the center A is 0, and the CNs are 1 over n factorial. So the center is always kind of where you pin your function down, right? Even this guy is correct at 0, at the center. And then the convergence kind of happens around that. So in order to get a good approximation using your partial sums, you still have to stay close to the center, right? So the convergence still happens around the center. But it is true that the interval of convergence here is all real numbers. So if you use the full infinite series, no matter what you plug in, is going to work. It's just that the further you are from the center, the more terms you need in your series for your approximation to be good. Dalton asks an interesting question. Is this similar to a Fourier series? So the big difference between these series, power series, and Fourier series is that power series start at a point, the center, and then the convergence kind of folds around the center. Fourier series start with an interval, and the convergence is uniform on that interval. That's the big difference. Here you have what's called pointwise convergence, and in a Fourier series, you have what's called uniform convergence. They're very different animals, but it's the same sort of thing that's going on. So that's a wonderful question. And the difference between Fourier series and power series is with a power series, you start at a point and you kind of fold up around that point. For a Fourier series, you start with an interval and you wiggle around a bunch, but your wiggles get smaller. And so the convergence is uniform. Google pointwise convergence versus uniform convergence for more information. All right, so this is a really big deal in real analysis. Uniform convergence versus pointwise convergence is a huge thing to comprehend, but it is not something we will be considering in this class. So really what we're doing with these series is we're talking about sequences of functions. You know, the first partial sum, the second partial sum, the third partial sum, the fourth partial sum. Each one of those partial sums is a polynomial. That sequence of polynomials is what we're considering converging. And for a power series, the convergence is pointwise. For a Fourier series, the convergence is uniform. In both cases, you have an infinite series being equal to a function. It's just the mode of convergence is different. That's a wonderful question. Okay, so I think we are almost out of time. I do want to hit you with one fun question before we bounce. So let me come back to this. I'll use this space down here. Suppose the power series sigma n from 0 to infinity Cn x to the n converges when x is equal to -4. Does sigma n from 0 to infinity Cn times 2 to the n converge? So all of this is section 11.8, and section 11.8 focuses on the idea of the shape of the interval of convergence. So to answer fun questions like this, and if you looked at the review in chapter 11 leading up to test 2, you may have seen some questions like this. Dalton, the center was 0. There was a center and the center was 0. So the center comes from the algebra of the series. The center in that previous sum was 0 because x to the n is x minus 0 to the n. So there's always a center. Every power series has a center. It's the point that the partial sums start folding around. But let's think about this. We've just got a few minutes here, so let's think about this. Suppose the power series sigma Cn x to the n converges when x is equal to -4. What can we say about the series Cn 2 to the n? In other words, can I say anything about the interval of convergence from this? The series converges when x equals -4. This implies, or really it's the same thing as saying, it's equivalent to saying x equals -4 is in the interval of convergence. So what does my interval of convergence look like? Well, my series is centered at 0. This series is centered at 0 because it's just x to the n. And I know that when you plug in -4, you get a convergent series, which means that R has to be at least 4. And since the interval of convergence is symmetric, I know that I can go at least 4 this way and stay in the IOC. 2 is right here. So my IOC is at worst the smallest possible IOC would be left closed, right open, -4 to 4. Because the IOC is always symmetric about the center, and I know that -4 is in the IOC. So my worst case IOC, it doesn't extend beyond this, but it includes this, which means it has to include everything up to here. In particular, it has to include 2. Therefore, sigma Cn 2 to the n must converge. These are fun questions. These are hard questions that require you to think very carefully about the shape and possible size of the IOC. Remember, IOCs are always symmetric. About the center. Except at the endpoints, right? You might include one, you might not include the other. But if you can go left 4 and stay in the IOC, then you can go right 4 and stay in the IOC. Maybe my IOC is -5 to 5. Maybe it's -infinity to infinity. But whatever it is, it's known to contain -4, which means it has to contain everything between -4 and 0, and it has to contain everything between 0 and +4. I know it contains this guy, so I have to have, worst case scenario, a square bracket here, but maybe it doesn't contain this guy. But no matter what, it contains everything in between. So it must contain 2, and this is what you get when you plug in x equals 2. I'm not sure I follow the question there, Ryan. If you told me that a priori that this series converged, I could not conclude that the series with -4 plugged in converges. But I could conclude that the series with 1 plugged in, or -1 plugged in, or 3 halves plugged in, or 1/2 plugged in, all of those would have to converge. So my worst case IOC, that's the way to think about these problems. Given the information they tell you, what is the worst case IOC? What is the smallest possible interval of convergence given this information? Since my series is centered at 0 and is known to converge when x is -4, my worst case IOC is this. I know that the radius has to be at least 4. The smallest possible interval of convergence centered at 0 with radius 4 is this guy. No, the center is just an algebra thing. X to the n is x minus 0 to the n. So TFD, we don't really use that a lot with power series. TFD is not super relevant here. So yeah, x minus 0 to the n is the same as x to the n. So my center is 0. All right. So next time we're going to talk a little bit more. I'll do maybe one more problem like this where we've got a fun question about shapes of intervals of convergence. And then we're going to start talking about how to find power series for functions. So representing a function as a power series. In other words, how did I know that this was arctan? How did I know that the other one was e to the x? That sort of shit. And it's going to start by working with geometric series and rational functions. And then we're going to develop what's called Taylor's theorem. So it would be wise for you to read section 11.9. 11.9 is one of the hardest sections in the book. People do struggle with it, so please read 11.8 and 11.9. Wednesday, we will do 11.9, which is a hard section. So if you read it ahead of time, that will help you a lot, because you're going to read it and you're going to be like, what the fuck is half of this stuff? But you'll at least have seen it. So when I start writing the things down on Wednesday that look scary as hell, like integrals of power series, it won't be as intimidating. I can show you really quick what I mean by looking scary as hell. So this shit looks scary, right? You've got an integral and then a series, or you've got a derivative and then a series. You've got these crazy things like Bessel functions that look fucking terrifying. You've got like integrals of series written out. It's a little bit scary. Here you're going to see the arctan series that we used. So please read 11.8 and 11.9. 11.8 has more discussion of the sort of stuff that we were doing today. Intervals of convergence and whatnot. It is, yeah. So this is the stuff that scares people about this class, but it's the good stuff. So you should check it out, right? Read this and then work on the homework. The homework is going to be just the sort of stuff we were doing in class today. Lots of ratio tests and endpoint testing. The applications to physics here are really cool, right? Like you've got a vibrating drum surface. How does that work? All sorts of neat things are very important for this. So I think you guys will enjoy this stuff if you put the time in, but you must dump massive amounts of time in. Power series, definitely the hardest part of the class. We'll be done with it by the end of this week, and then series will go away. You won't have to be afraid of series, or you won't have to mess with series much beyond this week. But of course, it's going to be on exam 3. It's going to be on the final, and exam 3 is going to come fast. All right, so we don't have a lot of time left in the term. This week, we're going to wrap up power series. Next week, we're going to talk about applications, and then I think we're pretty much done. I think that's pretty much it. So quick reminder, your final exam and the last day of class, all that stuff is not too far off. The last day of class is August 7th, right? So that's next Friday. So this week, power series, next week, applications, which is like parametric and polar stuff. And then you'll have a little bit of time to study for the final, because your final is on the 11th. So you'll have just that weekend to study for the final. And then that's it. So we're almost done with the class. Keep working hard. I'll get your exam 2s graded by this Friday. Exam 3 is going to be on the last day of class, and then the final will be the following Tuesday. All right, so I got to duck out and get over to my office hour. I hope you guys have a lovely afternoon. The new homework is going to drop a little bit later today, so take a look at that. And that is it. I'll see y'all either in office hours or on Wednesday. Oh, and if you need a makeup test, if you missed the test, email me. Even if we already talked, email me.